This lifespan began roughly 4.6 billion years ago, and will continue for about another 4.55 billion years, when it will deplete its supply of hydrogen, helium, and collapse into a white dwarf. But this is just the abridged version of the sun's lifespan. As always, God, or the devil, depending on who you ask, is in the details. To break it down, the sun is about halfway through the most stable part of its life. Over the course of the past 4 billion years, during which time planet Earth and the entire solar system was born, it has remained relatively unchanged. This will stay the case for another 4 billion years, at which point, it will have exhausted its supply of hydrogen fuel. When that happens, some pretty drastic things will take place. The solar surface showing active regions and magnetic loops. Nuclear fusion, the source of all the energy so generously radiated by the sun, does two things. It converts hydrogen into helium, or rather, makes helium nuclei from protons, and it converts mass to energy. The mass to energy conversion is described by Einstein's famous equation, E equals mc2, or, in words, energy equals mass times the square of the velocity of light. Because the velocity of light is a very large number, this equation says that lots of energy can be gained from using up a modest amount of mass. The energy created by the fusion processes within the core of the sun, or any other star, exerts an outward pressure. Unless contained, such pressure would produce an explosion, as happens in the hydrogen bomb, on a much smaller scale. The inward pressure that keeps a star from exploding is the gravitational attraction of the gas mantle surrounding the core, which is most of the volume of the sun, and is very hot but does not burn itself. The outward pressure from the fusion reactions keeps the stars from collapsing. The inward pressure from gravitation keeps the stars from exploding. If the fusion reactions in the core become too weak, a star can and does collapse. Such collapse can provide new conditions in a core that result in new types of fusion reactions, so that expansion follows. If fusion reactions in the core become too strong, a star can and does explode. Such events can be observed. When a star explodes, it shines with extreme brightness for a while. It turns from an unnoticed to a new star, a nova. Stars, like our sun, where inward pressure and outward pressure is nicely balanced, fluctuate but little in brightness and give off a steady stream of energy.